Okay, welcome to the lecture number 42. We have been discussing about the spin stabilization of the satellite. So, in that context we derived these equations, and these two equations then we combined into one, and this one then has been written in this format. So, what we were discussing that for this kind of system asymptotic stability can be ensured if A is greater than 0, B is greater than 0 and C is greater than 0. But in the present case, B is this is not B is not positive definite. Okay. So, these are greater than 0 implies this is positive definite. Okay. So, B is not less than 0, but this is also not positive definite. Why? Because if we look here in this particular term. So, this the initial entry this is 0, the first entry here. So, if know that from the Sylvester criterion for any matrix, say A equal to or let us name something else B C, let us name it as D. So, D equal to D 11, D 12, D 21 and D 22. For this matrix to be positive definite, it is required that D 11 should be greater than 0 and also the determinant D 11, D 12, D 21 and D 22, this should be greater than 0. So, at least this condition it is not satisfied here in this case, because here this entry is 0, okay, and therefore, we cannot ensure asymptotic stability of the system. However, this system still can be stabilized, because as I told you earlier, this term is appearing, this B here, this is not a damping term, rather it is a gyroscopic coupling term, and because of this the stability can be ensured, but not the asymptotic stability. For the asymptotic stability, the strict requirement will be that B should be greater than 0, which is not the case here. Okay. So, we continue discussing with this. So, let us pick up this equation, the first equation. Okay. So, the first equation we can write as, if we take the Laplace transform of the equation 1 and 2, equations 1 and 2. So, these two equations we are going to take the Laplace transform of them. So, this will yield s square alpha 1 s. Okay. So, for shortcut I will remove this alpha 1 s and I will simply write this as alpha 1, assuming that alpha 1 is nothing but alpha 1 s here. Okay. So, I need not put this extra, because it is a function of s. So, I am not going to indicate this for the simplicity. Okay. And thereafter, rest of the terms we can write for this equation. So, the other terms in this equations are minus 1 plus k times omega s plus 2 omega 0, and then alpha 3 dot. So, this will be s times alpha 3, again alpha 3 here is nothing but alpha 3 s. And here this also the Laplace transform, this will be nothing but alpha 1 s. So, this equal to 0. So, these two terms can be combined together. So, this will be s square plus 3 k minus 1 omega 0 square minus one plus k omega 0 omega s and then we are going to take alpha 1 outside, this minus 1 plus k So, alpha 1 and alpha 3 terms we have separated out. Similarly, Laplace transform of equation 2 yields s square and then there the first term is alpha 3 double dot. So, this becomes alpha 3 1 plus k and then again we combine the terms. So, the first term will be 1 plus k omega s plus 2 omega 0 this term alpha 1 plus s square minus alpha 3 this equal to 0, this is the equation number 6. So, what we can do that in this equation 5 can be rewritten as we take omega 0 square common out of this. Okay. S by omega 0 square omega s by omega 0 here times alpha 1 and minus omega 0 square if we take it as common. So, this will be 1 by k omega s by omega 0 plus 2 and here we will write as s by omega 0 times alpha 3. So, this equal to 0 and we see that omega 0 this quantity is not equal to 0. So, therefore, we can remove it and let us write s by omega 0 as lambda. So, this becomes lambda square plus 3 k minus 1 minus 1 plus k, there is a bracket here 1 plus k omega s by omega 0 we write as omega s cap. This is a non dimensional quantity. This is the spin rate which we have non dimensionalized. So, this we write as omega s cap times alpha 1 minus In the same way, here we will have 1 plus k times omega s cap plus 2 times lambda times alpha 3, this equal to 0. This is equation number 7. Following the same line of treatment, we can reduce this equation number 6 . So, we will get here equation for the equation 6, 1 plus k omega s plus 2 omega 0, 1 plus k omega s omega s plus 2 omega 0. So, this becomes 2, and the other term, this term here we write as s by omega 0 times alpha 1, s by omega 0 times alpha 1, and omega 0 will write here as omega square. So, 1 omega 0 will we can cancel 1 once inside the bracket, 1 here in this place. The other term, this is s square. So, here also omega 0 square we can take it outside. Then this is plus, here it is minus omega 0 square. So, this is minus sign here. So, this becomes 1, okay. This term it becomes 1, and we get here omega s by omega 0. So, this is omega s by omega 0 times 1 plus k. And then finally, we have here alpha 3. So, alpha 3 is taken out of the bracket, this equal to 0. So, what we see that because this quantity this is not equal to 0. So, we can eliminate and we can write this equation as 1 plus k omega s cap plus 2, and this quantity we are writing as lambda. So, this is lambda times alpha 1 minus lambda square minus 1 plus omega s cap 1 plus k this equal to 0. So, we have these two equations in alpha 1 and alpha 2. So, we can get the eigenvalues from these two equations, or we say for the non trivial solution we can the determinant formed by this, it should be equal to 0, and that gives us the required eigenvalue equation. So, we combine both of them together. So, combining them together, let us go back. This is the first term here, okay, lambda square 3 k minus 1 lambda square plus 3 k minus 1 3 k minus 1, and then minus 1 plus k omega s cap omega s cap. Okay. So, this is the first term. The second term arises here in this place, which is with minus sign. So, here we will get here minus lambda times this lambda, okay, 1 plus k omega s cap plus 2 okay, and rest we pick up from this place. So, this is 1 plus k omega s cap plus 2 times lambda, and here this part becomes lambda square minus 1 plus omega s cap times 1 plus k. Okay, this should be equal to 0. Okay, so, these two equations have been combined together. So, for the non-trivial solution, like what we have done, that you take out alpha 1 and alpha 3, you can write it in the matrix format by alpha 1 and alpha 3, this equal to 0, because alpha 1 and alpha 3 is appearing here, and also it is appearing here in this place. Okay. So, यहाँ पर स्क्रीन पर कुछ प्रॉब्लम हो रहा है, वो स्क्रीन फ्लक्चुएट कर रहा है कभी कभी। वो स्क्रीन पर वो कुछ पूरा जैसे टीवी में होता है ना, उस तरह से पूरा कलर वो चेंजिंग पूरा हो रहा था।
सर सामने टीवी में?
हाँ, टीवी में।
सर वो टीवी में प्रॉब्लम है सर, यहाँ रिकॉर्डिंग एकदम।
अच्छा, ठीक है, ओके, ठीक है। Okay, so for the non-trivial solution for this kind of system, the determinant of this matrix must be equal to 0. So, this is what we are doing, and from there we get this eigenvalue equation here, or say the eigenvalue polynomial. So, this part we have lambda square 3 k minus 1 plus 1 plus k omega s cap 2, this is fine. This equation you can check that here it is the same entry, here it is with minus sign, while here the sign is not there, and this is lambda square 1 plus omega s plus k. Okay, this is fine. So, let us assume that this quantity is k 1, and we assume that this quantity is k 2. So, this will help us little bit reduce the problem. So, we can write this as lambda square plus k 1 minus lambda times 1 plus k omega s cap plus 2 this equal to 0. Now, if we expand this, open up this determinant and write this equation. So, we get a 4 degree polynomial in lambda. Okay. So, this k 2, what we will do, we will put here a plus sign. So, that we include this sign here also, there is a minus sign here. So, in the k 2 we will include this sign. So, that will make it little bit more coherent. Okay. And then here then this becomes plus lambda square times 1 plus k omega s cap plus 2 whole square. And this quantity will be equal to 0. So, we have here lambda to the power 4 plus lambda square times k 1 plus k 2 and k 1 k 2 plus lambda square times 1 plus k omega s cap plus 2 this whole square, this equal to 0. Lambda to the power 4 this part, and then lambda square term appears here, lambda square term appears here. So, we add both of them. Okay. So, the lambda square k 1 plus k 2 plus 1 plus k omega s cap plus 2 1 plus k omega s cap plus 2 this whole square, okay, plus k 1 times k 2, this equal to 0. So, if you look here in this equation, so this appears like lambda to the power 4 plus b 1 times lambda square plus b 2 time plus b 2, okay, this equal to 0, where b 1 equal to k 1 plus k 2 plus k omega s cap plus 2 this whole square, and b 2 is k 1 times k 2. Okay, this can be expanded and this can be reduced. Okay. So, we have b 1 equal to k 1 plus k 2 plus k whole square. So, if we insert the values for k 1 and k 2, this we have written as k 1 and this we have written as k 2 with minus sign. So, this becomes 3 k minus 1 and then minus 1 plus k omega s cap minus 1 plus k omega s cap. Okay. So, this is the k 1 term, and k 2 term we have 1 plus omega s cap plus 1. So, there is a minus sign ahead of this. So, here so this will appear with a minus sign, the minus sign is here. So, 1 plus omega s in the bracket 1 plus k times omega s cap plus 1, okay, 1 plus omega s cap 1 plus k. Okay. So, this is what we have written here, and of course, the other terms we can expand it. So, if we expand, this will be 1 plus k whole square omega s cap square plus 4 plus 2 times 1 plus k omega s cap. So, 2 into 2, this makes it 4, 1 plus k omega s cap. Okay, and then we can rearrange the terms. So, this is 3 k minus 1, here this term and this term both are having the minus sign. So, 3 k minus 1 minus 2 times 1 plus k times omega s cap, okay, and then this term comes with minus sign here plus 4 times 1 plus k omega s cap plus 4. So, this term we can look into this, this term is a separate one. So, this becomes, and here we have minus 1 minus 1. So, this becomes 3 k plus 2, if we take into account this. So, 3 k plus 2, and from this place we will have 2, and this is plus, this is coming with a, this coming with minus 2 sign, this is but plus sign. So, this becomes 2 times 1 plus k times omega s cap, okay. And lastly, we have this term plus 1 plus k whole square omega s cap. So, this is your B 1 term. So, if you remember that in the gravity gradient topic, we got the same kind of equation. Okay. We exactly got the same kind of equation. So, for stability, we must have, we have discussed it in detail. So, I will avoid again repeating the same thing. For a stability, we need that B 1 should be greater than 0 and B 2 should be greater than 0. In addition, we should have B 1 square minus 4 B 2, this should be greater than 0. So, this is what for the gravity gradient also we have written, and I have explained it in details why the V 1 and V 2 all these things need to be 0. Okay. And as you see that here in this case, the coefficient of lambda q term is not there, it is a 0, it is a coefficient of lambda q term, this is 0, and coefficient of lambda term, this is also equal to 0. So, for this kind of system, if we want that all the roots they are lying on the negative real axis, okay. So, there should not be any sign change here in this polynomial, and all the coefficients must be present, but here in this case this is those coefficients are 0. This way we have discussed and detailed it. So, I am taking it for granted that you have gone through the earlier lecture. So, now if B 1 square minus B 2 4 B 2, this is greater than 0, and this quantity, if these are satisfied, then the system will be stable, but not asymptotically stable. Again and again I am repeating, because in this case we do not have the B matrix, the capital B matrix we have written this B matrix. This B matrix is not positive definite. Okay. As you can see here, this is not a positive definite matrix. So, we cannot ensure asymptotic stability here in this case, but at least we can ensure that this system remains stable, means the once you disturb the system from the equilibrium state, the disturbances they remain bounded. Okay. And for that, these conditions must be satisfied, that B 1 is greater than 0, B 2 is greater than 0, B 1 square minus 4 B 2, this is also greater than 0. Okay. Now, we look into this omega cap term, which we have defined as omega s by omega 0. Let us assume omega s equal to 1 rpm, 1 rotation per minute. Okay. And omega 0 if it is a 90 minutes orbit, so that implies 1 by 90 rpm for a 90 minutes. Just a minute. एक लेक्चर में हूँ, मैं कॉल करता हूँ आपको बाद में. अभी तो रिज्यूम कर रहा हूँ.
हाँ सर.
For 90 minutes orbit, okay, so omega 0 will be 1 by 90 rpm. So, omega cap in that case becomes 1 by 90. So, this is 90. Okay. So, in general, or say as the altitude of the orbit increases, omega 0 will decrease accordingly. And this implies that omega cap, this omega S cap we have written. So, omega S cap, this will grow in magnitude. Okay. And as you remember that omega S, the spin rate, this can be positive or this can be negative, because the satellite is moving here in this orbit, here in this direction, and your one axis is here, or x 0 we have taken here in this direction, while the y 0 is along this direction and z 0 is toward the center of the. So, this is your orbital axis system. So, here in this case your if omega s, here in this case what we have taken, that our this is the direction of omega 0, okay, while this is omega 0 here, okay, while your omega s we have taken in this direction. So, this is a positive omega s. Omega s can be negative if the rotation is this way, if the spin rate is this way. So, this is negative omega s. So, omega s can be both positive or negative, but if the as the altitude increases. So, the magnitude wise, if we take it magnitude wise, this is not a, I am not showing a vector, this omega cap just we have indicated for the indicating this as a non dimensional number. So, cap it does not indicate a vector here in this place, this hat, this is not a vector notation. Therefore, here in this place, as we see that as this omega the altitude increases. So, this quantity will keep decreasing as the altitude of the orbit increases. This is the separate word here, increase, orbit increases. So, omega 0 will keep decreasing accordingly in magnitude, okay, and therefore, and this implies omega s will go up, it will become larger and larger in magnitude. Okay. So, now we can discuss about the stability part again. So, in general, omega s cap will be large in magnitude. Okay. Now, let us take one example. Let us say that let k equal to 1 and omega s cap this equal to 4. Okay. So, accordingly we can calculate this matrix, the B matrix. If we go back for k equal to 1 and omega s equal to 4, this is your B matrix, okay, and this is your C matrix. So, k equal to 1 and omega equal to 4. So, I will write here in this place. Okay. So, the B matrix becomes if k equal to 1. So, this remains 0 and here k equal to 1, this is 1 plus 1 2 on omega S cap we are taking. So, I will assume that it is already divided and therefore, this is minus minus 8 and plus 2 minus 10, this becomes minus 10 and this is of the opposite sign. So, this becomes 10 and this is 0 and accordingly the C matrix, this is k equal to 1. So, 3 minus 1, this is 2 and this is omega square we have already eliminated. So, I will have to do it here, otherwise this part we are eliminating. So, 3 minus omega S cap we are taking equal to 4. So, 3 k minus 1 k equal to 1. So, this is 2 and then minus 1 plus k, this is 2 into omega S cap. So, we get here 4. So, this is minus 6. So, this is minus 6 and this element it is 0 and this is 0 and here in this place we will have omega 0. So, here this will appear as 1, this term will become 1 and omega S cap. So, this is plus 4 times k equal to 1. So, into 2, 4 into 2 8 plus 1, this is 9 and this with a minus sign. So, we put a minus sign here. So, once we are taking this example, this is 0 10. Okay. So, we go back to the, so B equal to 0 minus 10 and 10 0 and C turns out to be minus 6 0 0 and minus 9. So, for this we can get the eigenvalue of the system. So, your the first matrix A is nothing but 1 0 1 1 and 0 0. Okay. So, directly also we can write the eigenvalues like this. So, determinant of, we have to take the determinant of this quantity, this is 1 0 0 1 and plus lambda times 0 minus 10 10 0 and plus this term minus 6 0 0 minus 9. So, this way also we can get the eigenvalue equation. So, from here just what we are doing, that this is your A matrix, this is B matrix, this is C matrix and the corresponding double differential term has been replaced by lambda square, single differential term by the second differential term by lambda square, first differential term by lambda and the, because here there is no differential term. So, nothing is appearing here. Now, if we expand it and write it, so this becomes lambda square. So, add all of them. Okay. So, we have to take the determinant of this becomes lambda square minus 6 and from this place we get minus 10 lambda and this will get accordingly 10 lambda and this will turn up with lambda square minus 9. Okay. So, for this we need to take the determinant. If you now solve it, so this gives you lambda to the power 4 85 lambda square plus 54, this equal to 0 and the values of the roots, then lambda will be plus 9.18 I and minus 9.18 I. The other set will be 0.80 I and minus 0.80 I. So, what we see that all these 4 eigenvalues, they are lying on the imaginary axis. As I told you that this system cannot be asymptotically stable, it is not possible, because your B matrix, this is not positive definite. Okay. If it is positive definite and this is also positive definite, then only we can say that the system is asymptotically stable. So, here in this case this is not positive definite, but still what I want to show that. So, this is statically not stable, okay. Statically unstable, okay. But because of this term, this B term, which is the gyroscopic term, okay. So, your eigenvalues, if this term B, suppose that B term was not present. So, in that case we will have only the C term, and with C term, because it is a not positive definite, you can see that this is negative definite, because this part this is 6 minus 6, the first term, this is negative, okay. Therefore, this is not positive definite, and therefore, only with C term your system cannot be stable, and as you know that only if C is present. So, we can write our equation x double dot minus 6 times x tilde this equal to 0. So, you know that this is unstable, okay. And similarly, the other part can be written as x say this is x 1 double dot and this is x 3 double dot minus 6 minus 9 x 3 tilde this equal to 0. So, this is also unstable, but because of this term which is present, this is also not positive definite, but a proper choice of the values here, okay, that can ensure that finally your eigenvalues do not lie in the right half complex plane. So, here the eigenvalues are not lying in the right half complex plane. So, this will be visible, let us expand it here and then write. So, this will also give us certain insight. This is lambda to the power 4 minus 15 lambda and plus 54, and from here we get minus plus this becomes 100 lambda square, this is lambda square. So, what we can see that this is a negative term and here this is a positive term. If it so happens that if we choose the values of omega s and k such that these two terms together become negative, okay. That means, in this equation if this coefficient becomes negative, okay. So, in that case your system will become unstable, okay. So, by choosing properly the values of k 1 k and omega s cap, we can ensure that the system remains stable. So, in this case the system is statically unstable. We say it is statically unstable because this the stiffness part is not positive definite, okay. But this gyroscopic term, this happens to support this case and this pulls out of an instability this particular system, okay. So, now, we can plot this equation, and if we plot say the k 1 we have 3 k minus 1 minus 1 plus k times omega s cap, this should be greater than 0, and k 3 1 plus k times omega s cap plus 1, this should also be greater than 0. Why this should be greater than 0? Because these are the terms which appear in this matrix. This term we are writing as k 1 and this term we are writing as k 2. Okay. So, k 1 times k 2 this should be greater than 0. So, what k 1 times k 3 we have written here k 2 or k 3, just this we are written, this is k 3 term, okay. This we are writing as k 3. Okay, k 1 times k 3 this should be greater than 0, and anyway for the C matrix to be positive definite, it is required that k 1 should be greater than 0, and also the minor this k 1 0, 0 here k 3 this should also be greater than 0. So, this implies that k 1 k 3 this should be greater than 0, because k 1 is greater than 0. So, k 3 is also required to be greater than 0, means both these quantities need to be greater than 0. So, one requirement is that this must be satisfied, k 1 times k 3 greater than 0, as we have written earlier that this B 2 is greater than 0. This implies k 1 is greater than k 1 k 3 is greater than 0, k 1 times k 3, and this also implies that k 1 should be greater than 0 and k 3 should be greater than 0. It cannot be, this can be greater than 0 even if k 1 is less than 0 and k 3 is less than 0, both are negative. So, in that case also this can be greater than 0, but that will violate the requirement here that k 1 is greater than 0 and similarly k 3 greater than 0. So, therefore, that case is ruled out, only this is acceptable, that k 1 and k 3 both of them should be greater than 0. So, B 2 greater than 0, this implies that k 1 is greater than 0 and k 3 this is greater than 0. In addition, we have B 1 square minus 4 B 2, this should be greater than 0. Okay. So, taking this we can plot it, okay. B 1 greater than 0 and B 2 greater than 0, and this part we can plot, okay. And if we plot, so the plot will look something like this. So, the here is a graph for see what we have the graph. So, this graph is plotted here. This is a figure from Peter C. Hughes, and this is a book on spacecraft dynamics. But this book is almost unreadable. Okay. So, I have taken this figure from that place, and I will show you what does this mean. So, this delta is basically B 1 square minus 4 B 2, this equal to delta. So, this curve here it is a plotted for the first curve it is being shown. So, this curve. This is plotted for delta equal to, set this equal to 0 and then plot it by giving the B 1 and B 2, these are functions of k and omega s cap. So, here instead of nu cap we have used this omega s cap, and here this is written as k t, but we are using this k term here, and k is nothing but I 0 minus I divided by I, and as we know this k will lie, as from our gravity gradient discussion, this k always lies within the range minus 1 to plus 1. Okay. This small k 1 is a slanted k 1 is shown, this is nothing but your k 1, and this is your k 3 as we have previously discussed, and this is your B 1, B 1 equal to 0. Okay. So, here it is showing k 3 this equal to 0, this curve, and this value is minus 1 by 2. It is not given here, but if you put the, say here it is on the right hand side, okay, and your k 3 equation if you put in that. So, k 3 equation we have written as minus 1 plus k times omega s cap. So, this point we are picking up here in this place, okay, and k 3 equal to 0. So, this line it is being shown that this line is k 3 equal to 0. So, this line is running from this place and it is going like this. So, this is your k 3 equal to 0, which is shown here by this red one, okay. And this line is for k 1 equal to 0, and this line comes like this, and both of them cut on this y axis on the omega s cap axis. So, this is their cutting point, and this particular line b 1 equal to 0, this is not of interest to us. Okay. So, if you set k 3 this equal to 0 and solve this, okay, here k equal to 1, we are taking it on the right hand side, extreme right. Okay. So, if you take k equal to 1, put it here. So, this is 1 plus 2 omega s cap, this equal to 0, and that implies omega s cap will be minus 1 by 2. So, this quantity here, this is minus 1 by 2, okay. And then it cuts this axis here in this place. So, for this part k will be equal to 0. So, set k equal to 0 in this equation, and that will give you the value of how much the omega s cap will be. So, here if you put that, so this point it will have a value of minus 1. Okay. So, this is minus 1 here. Okay. The point where this curve and this particular curve, both of them cut, okay, here in this place, this value is minus 1.5. Okay. Accordingly, you can look into this. Okay. Now, so you know that what these graphs are standing for. Okay. So, this is, let us go on the top and look into this figure. Okay. This figure we cannot look because okay, first we will discuss it here and then we will take that figure again on a new page. Okay. So, here if you see now we look into our requirement. On this side, k 1, k 3, k 1, k 3, and here also we will have the k 1 and k 3. So, what are the values of k 1 and k 3 in this region? On this line k 1 is 0, on this line k 1 is 0, on this line we see that k 3 is 0. So, what about this range? So, here the range which is shown, and this range, this one is your b 1 square minus 4 b 2, this equal to 0, okay, which is written here as delta. So, here k 3 is less than 0 and k 1 is also less than 0, while here in this range k 1 is greater than 0, k 3 is also greater than 0. In this part k 1 is greater than 0 and k 3 is less than 0. Okay. This you can just check by putting various points in this region and in this region, so on. Similarly, here the quantity delta, this will be greater than 0, while here in this range delta will be less than 0. So, which is shown here, this bounded line like this from this place. So, now we can conclude few things. This k 1 greater than 0, k 3 greater than 0, this is a requirement for static stability. So, in this region your static stability is ensured. So, this region is statically stable. Okay. While this region, what we see that k 1 is less than 0 and k 3 both are less than 0. So, this is statically unstable, means stiffness is not there. Okay. However, this delta is greater than 0 and this delta greater than 0 means B 1 square minus 4 B 2, this quantity is greater than 0. So, if this quantity is greater than 0, so this region becomes gyroscopically stable. While this is statically unstable. Because k 1 and k 3 both are less than 0 here in this range, and here k 1 k 3 are greater than 0. So, therefore, the static stability we can say that the system is statically stability as per our earlier discussion. So, for the eigenvalues we also we must have for the gyroscopic stability B 1 square minus 4 B 2, this should be greater than 0. So, even if your system here you can see that even if this is the static stability is not satisfied, but if this quantity this is satisfied, then the system will be gyroscopically stable and also this will be directionally stable. So, what does mean by directionally stable? We can discuss it in the on the next page. So, this is also directionally stable. Similarly, this part we will have the directional stability, y we will take it bit afterwards. Okay. So, we can go on the next page and look into the figure. So, this figure it is showing you that this is from minus 1 to on this side this is plus 1. So, k value is ranging from minus 1 to plus 1, while omega s cap is ranging from minus 5 plus 5 here on this side to minus 5 here on this side. Okay. Now, we take this figure. So, this figure what you are showing is seeing here. So, this is here as you can see this cursor is okay. As you can see that nu cap or the omega s cap is here minus 50 and on the downside you can see that minus it is a minus 50 here in this place. The k value does not change, k is from 1 to minus 1 on the left hand side. Okay. So, the figure what we have seen here in this place, this is a expanded figure near origin. So, this has been expanded near origin means you can see that this minus 1 to minus 1 range, but here on the y axis it is a plus 5 to minus 5, while here it is minus 50 to plus 50 on the y axis. So, if you expand the region near the origin or say region near the x axis, then you get the figure which is shown here in this place. Okay. So, these are the figures drawn using the same thing like we have discussed earlier. Okay. So, this figure these are the boundaries that we are seeing here. Okay. So, while it is not visible here, you can see this small portion here. So, this portion it is indicating the same line. This is your delta V 1 square minus this delta equal to 0, it has been plotted. Okay. While here on this side your k 1 and k 3 it is plotted, which is not visible. So, this region it is written here directionally stable, statically stable, statically unstable and gyroscopically stabilized. So, k 1 times k 3 this is less than 0 and therefore, it is statically unstable. Okay. While directional stability, I told you that we will discuss this, what does mean by directional stability. So, your satellite is rotating like this, okay, it is spinning. Okay. So, as we have looked into that I 2 times theta 2 double dot this quantity is 0 or I 2 times we have got in terms of this. Okay. And where omega 2 is the absolute spin rate about the 2 axis. So, 2 axis is going inside here into the page. Okay. So, this can be written in terms of theta 2, the other term we have as you remember that omega s the spin rate, this is nothing but omega 2 plus or omega s plus we have written omega s plus omega 0 equal to omega r, the relative velocity with respect to the orbital axis. And this is the quantity which is responsible for giving you theta 2. Okay. So, theta 2 is measured from, this is the Euler angle which is being measured from the second axis of the orbital reference frame. Okay. So, for this part, if the satellite is rotating like this, so what we can see that if we this equation we can write in terms of, obviously if we differentiate this. So, this quantity we can write as omega s is your omega 2, this is the absolute angular velocity, the spin rate, and plus omega 0 equal to omega r, which is nothing but your theta 2 dot. Okay. So, if we differentiate this, so omega 2 dot will be equal to theta 2 double dot, because omega 0 we are taking a circular orbit. So, omega dot 0 this will be equal to 0. Okay. So, therefore, this can be replaced by this equation, and in this equation what we see that if we do little bit of change in theta 2 dot, okay, this is the change. Okay. So, means you are changing the angular velocity here. If you change the angular velocity here, so because this on the right hand side you have this quantity equal to 0. So, this implies that theta 2 dot this will be equal to a constant. Okay. So, that means if you are changing this theta 2 dot by a small quantity. So, this quantity is not going to die out, this will remain. Okay. So, along the spin axis your satellite is not stable, means it is not stable in pitch. Okay. This is not along the we should not use the along term, we should say that this is not stable in pitch, means here if you create any disturbance, that disturbance is not going to die out, as I am showing by this particular arrow. So, this simply implies that the 3 axis stability of this system is not possible, because of this particular equation 3 axis stability it is impossible. Okay, because on the right hand side we are getting here 0, and this we have taken for the axisymmetric case, where k equal to I 0 minus I divided by I 0 is, say in the case of the cylinder, I 0 is along this direction and I is along this direction. So, but however, because as you can see that the spacecraft it is spinning, means if you look here in this part. So, here say this is your satellite, this is a cylinder and it is like this. So, this is the orbital plane, okay, and satellite is rotating like this. Suppose if the satellite is rotating like this, so its angular velocity vector will be along this direction. Okay. Let us see here it is a visible. So, angular velocity vector, suppose here it is along this direction, depending on the orientation obviously. So, this is because of the spinning. So, as you know that if something is spinning, and I will show you one video from YouTube in the once we start the next topic. So, this can, if you disturb it, okay, little bit, if you disturb it, so it will start precessing, okay, but it will remain bounded. Okay. So, that it says that this kind of system which is rotating about one of the axis, okay. Say in the case of the top, if we take the case of a top is rotating on this axis, okay, and if you tilt it little bit. So, what it happens, the torque due to gravity comes into picture, and because of that it is a continuously rotating. Okay. So, similarly, here in the case of the spacecraft, we have this in the orbit, and this is rotating on this axis. So, because of this angular momentum, this inertia is there. So, its each vector it will resist to any change. So, this directional stability is ensured, means it is a directionally stable, it will try to point out along this direction. Okay. So, therefore, it is written here this is directionally stable and statically stable, unstable because of this region, okay, and gyroscopically stabilized because in this region your delta is greater than 0, while here in this place delta is less than 0, therefore, this is gyroscopically unstabilized. So, directionally and statically stable. So, your k 1, k 3 this is greater than 0 here in this place, and therefore, this is statically stable, and directional stable, it is directionally stable here also in this place and here in this place also, and more the spin rate, more the directional stability will be, because then its angular momentum will be very high, and changing it by even a small amount, it will require a large amount of torque. Okay. So, therefore, in both these regions the system remains statically stable, and in both these regions system remains directionally stable. Here it is statically unstable, while here is statically stable. Here the gyroscopic stability is ensured, while here in this range gyroscopic stability is not there.
सर खत्म हो गया सर.
अब जस्ट एक मिनट खत्म ही हो गया. हो गया। ठीक है, फिर इसको वाइंड अप कर देता हूँ। अभी इसमें थोड़ा एडिट करना पड़ेगा इस पार्टिकुलर लेक्चर को। ओके सर, रिकॉर्ड करें।
हाँ सर।
Okay, so we have all discussed about the stability of the system. Now, there are two corrections here. Perhaps this part we missed in the while writing, this square was missing there. So, I have put this square. So, note down this correction here in this place. Okay. So, we end this lecture and we will continue in the next lecture with the new topic on we have finished the spin stabilization. So, remember that whatever we are doing, it is a elementary course, okay. It is not a very advanced course. We can have lecture on this satellite attitude dynamics for one more year and we will not be able to finish. Okay. So, we are just presenting a limited part, and in that scope keeping in view the undergraduate and the postgraduate requirement, but in the spin stabilization now as you know that we have taken the axisymmetric case. If it is not axisymmetric case, so obviously the system will be more complicated. I times theta, that is what we have got, that I times omega I 2 times omega 2 dot this equal to 0, this quantity will not be 0, okay, in that case. So, so we will have a complicated system in and it will be difficult to analyze also. So, we stop for the time being with this, and in the next lecture perhaps we are going to start with control moment gyros we have and the reaction wheels, or we say that one satellite is we are having one satellite, inside that one wheel is moving, and using that wheel or the satellite may have two parts, one part stationary, another part continuously rotating. So, we look into the stability of that kind of system and also how the control moment can be generated using the reaction wheels or the control moment gyros. So, this is topic of our next lecture. Thank you very much for listening.